If we, okay, but if we did, would you read the textbook? Very true, or you'd have to figure it out. Mhm. Why Reacher? Reacher's a serious one. Okay. Anyway, let's continue with this stuff. Well, you're not, but that's the thing. You're not there yet. Just don't get there. It's like I can tell you from my hometown, we like you also need to consider things like when you get two intelligent people together, they plan things out like starting a family and when to have kids and why to have kids. And but I can tell you from my hometown in Redneck, USA, Cletus and Velveeta down the street are popping them out like rabbits. It's just
I love working with cheese.
so. Educational programming for them is Maury. So, okay, so we got here, and we found that the vector we calculated actually follows the right hand rule.
Oh, I figured out. I'm looking at this stuff.
You can do it that way too. There's a number of ways you can do it. Well, I point my fingers in the direction of the velocity and I curve towards the magnetic field. So you notice here we did I L3 cross B, and we get that negative K hat direction. If you were to do the same thing with I L1 cross B, you're going to get a positive. Because if you go back to the loop, the current is the current across side 1 and side 3 are anti-parallel. Mm-hmm. So then, of course, if we look at the how do we do the magnitude of this? So you've been doing magnitudes for two-dimensional vectors. Yeah, you just add the third component in. So if you notice, we have 0 and 0 for the X and Y. Yeah. So we had the magnitude of this force vector. Now we're kind of thinking about this. So we have a force. What? Okay, so the force on this side is down. Force on this side is up. So you start to see why we're having a torque on this system. If you put a rotation axis right down the center, that's going to spin. This is the idea behind a lot of generators, a lot of motors. Okay, so now let's go back to torque. The generalized expression for torque is R cross F. Now, let's think about okay, so that's going to be R cross the magnetic force. And then if we think about, so if you look here, each one of these sides is B, okay? So if the axis of rotation is right here, what is the R value, the distance? The whole side, look, the whole side is B. If the axis of rotation is right here, what's the length of the rotation arm? One half B. So this is going to give us RFB. Let's see. So cross product is sine of theta. And so and again, let's look at these. What is the angle between the force and the rotation arm? Well, here, let me draw it to, yeah, 90 degrees. Let me draw it for you looking straight down the center. You have a rotation arm. Your axis is right there. Well, it's close. I mean, it's center. So like that. So yeah, each one of these, B over 2. Yep. So that's going to be the sine of 90 degrees. So that goes to 1. And we get R FB or B over 2 IAB. Now that's the force on one side. How do we get the total torque of this system? I was going to ask the same question. No, I heard you say torque and giggle. Oh, you did it. You weren't even here last semester. How did that transfer to you? Yeah. Really? Okay. Well, that's why I turned off comments. So the total torque. Of course you got blamed.
That makes sense.
Maggie wasn't here last semester, but apparently y'all have transferred that to her now. She's sitting between anger problem and spiral rider. So what are the two torques that are causing this rotation? Yeah, so we have the torque of side 1, torque on side 2. So we're going to get B over 2 IAB plus B over 2 IAB. That's going to be 2B over 2 or A times B times B. And and think about this rectangle. What is A times B? The area. So that's the area of your loop. Now, I'm going to try and think of this in a more generalized format. No, we're just like looking down the center of it. So we're gonna take. So we're gonna have this surface area vector that we've been talking about coming perpendicular off. Or cross-sectional area, because it's a loop, it doesn't really have a surface. That's making an angle theta. You have the force of magnetic force there. Magnetic force there. B over 2. B over 2. Then if you remember, we actually have to extend the torque arm out. And here we get theta and theta. Now, one thing we have to remember, do wire loops or coils typically only have one loop? No. So the first adjustment we have to make, maximum torque is going to be in IAB. Number of loops times that maximum torque. You can, or you'll be told. So this means that we now have a torque that's going to be number of loops times I. And now this time, instead of L cross B, what we have is the cross-sectional area of your wire loop cross B. Or NIAB sine of theta for the general sense. But we come across a new quantity.
What difference? This is foreign.
We have a new quantity. So Greek letter mu. This is the magnetic moment of the current loop. Yeah. So in vector format, it's that. Which means now that your torque becomes magnetic moment times B sine of theta, or the most general expression of magnetic torque. And your magnetic moment is always going to point in the same direction as the cross-sectional area vector. I put this one on here because it reminded me of some of you. You get caught doing things and you're like, well, that's not me. It's like, no, it was you. As the vector A, the cross-sectional area vector. Okay. Yeah. Now I put those offset from each other, but they're like, remember, your magnetic moment is also always going to be right at the center of your current loop. They would. Okay, now I'm going to switch to my other slides because that was no. Yep. Now we're going to work through this. You have two wire loops. You see the magnetic moment, and you see the magnetic field making an angle of 30 degrees with each other. One of them is a circle, one of them is a square. We need to figure out the torque on each of these. Okay, so part A is for the circular loop. So we know that torque okay, so we need to know what that mu value is. It is. And that's a single loop, so that's one loop. Yeah, but what's the area? So we can take that out. N is one, so it's I. What is the area? Mm-hmm. That's because that's what it is. Mhm. So when you plug your numbers into this, you should get a torque of 1.57. And what's the units of torque?
Um,
Amps times Tesla times meters squared. Oh, you're close. It's newtons times meters, which is what? Amps times meters squared times Tesla gives you the Newton meter, which is the what? The joule. Torque is an energy. It's always going to be in joules. Okay, so for part B, same current going through a rectangular loop that has 3 loops on it. Mm-hmm. Mm-hmm.
and your sign of that is 30 degrees. But they would-
Yes, 30 degrees. Because if you look back at the original cross product, that has to be the angle between the mu and the b. Mm-hmm. Remember, when you're crossing one vector into another, the theta is the angle between the two vectors. What is A for this second one? Yeah, length times width. Length, width, B, sine of theta. So that'd be what? That'd be two times 3. N is 3. 3. Your current is 2 amps. Your length. Yeah, it doesn't really matter which one you. 3 meters, 2 meters. Your B. Sine of 30 degrees. You should get 9.0 joules. So that is torque on a current carrying loop. So now let's talk about magnetic field due to an electric current. The magnetic field is this right-hand rule is fairly simple. If you have current running through a wire, you point your thumb in the direction of the current, your fingers wrap in the direction of the magnetic field. Yep. So between this and this section and the next section, we're going to kind of use the same. I mean, we're going to kind of go back and forth, but we're talking something here, like the book put this one first, which doesn't make sense, but we have to use Ampere's law. Okay, so yeah, you actually can. Yeah, it's just if the current goes that way, your fingers wrap in the direction of the magnetic field. So Ampere's law yeah, so that's your differential of your length or your path and mu zero, that's a new constant for you. Remember how we had epsilon zero and that was the permittivity of a vacuum for electric fields? Mu zero is the permittivity of a vacuum for magnetic fields. How much of a magnetic field would be permitted through the vacuum of space? Then I is still your current. And you remember Gauss's law, how we had to use Gaussian surfaces? Now we have to come up with hypothetical pathways called Amperian loops. Okay, so let's look. Let's just say we have a wire. Current going that way. What I'm going to do, yeah. I'm going to draw this circle. Just kind of going around the wire. This is my Amperian surface, okay? My Amperian loop. Now I know that this is, if I put directional arrows on here from the right hand rule, that this is in fact my magnetic field. But the way I'm looking at this is as I go along this pathway, I'm going to take these tiny little chunks, okay? because these are my infinitely small length elements, DL. Okay? Now, the thing to keep in mind about an Empyrean loop is, let me just go ahead and draw. Never quite get those. There. So I'm just going to go ahead and draw a loop, okay? And if I think about, that's my DL. My tiny little vector coming off of here that's my DL vector. It's just this little bitty vector for that tiny section. But I also know it's the same thing. I also know that at each individual tiny spot, if I make that path smaller and smaller and smaller, that magnetic field vector is also just a tangent line to the curve. Okay. Basic calculus. A differential is a tangent to a curve. Now, the reason this makes things easier for us is because what is the angle between those two vectors? 0. So Ampere's law is all based off the parallel magnetic field. Your magnetic field parallel to your length element. Okay. So we know, and this integral with the little circle around it, that is a path or a line integral. It's a closed path. That's what that indicates. So we have a closed pathway as we go around that circle. Okay. So my B dot DL becomes BDL cosine of theta BDL. So from there, we're going to figure out what DL is real quick, and then we'll call it a day. But so this time I'm just going to draw the same circle, but you're looking straight down on it. Okay. No. There you go. So you're just looking straight down on the path. You have your current coming out of the center there, and then what you have the radius of that pathway. Okay. Here in the center, or here along this arc, that's your DL. Okay. So if that's a differential, what do I have here in the center? Radius is going to stay what it is. So we have to figure out what L becomes. So what is that? What do I usually label that? Theta, but I've gone an infinitely small arc length. So what is that theta now? Yeah, so this is d theta. So instead of like delta L and being delta theta, we have dl d theta. So what that means, so first off, the magnetic field is a constant, so it pulls out of the integral. Now we're just going to draw a regular integral. And we have R. Oh, sorry. First, you have to know the arc length, dl equals R d theta. That's the arc length formula. Remember your arc length, S equals R times theta. So same thing. it's a constant. So R d theta, so since d theta is what we're integrating, because R is also a constant. What does theta go, so a whole circle, what is theta, it starts at 0 and goes to what? Or 2 pi. Those are the limits of your path integral. And so you'd end up with B R 0 to 2 pi d theta equals mu 0 I. And we'll finish this next time and finish the chapter. Yeah, the mu 0 is a constant. You would look that up. That is your permittivity of a vacuum for magnetic fields. That's your current. Well, that one, I want you to just accept that this is Ampere's law for now. Because in me kind of snapping, I just about gave you the full derivation from the Biot-Savart law. And I was like, yeah, I don't think we're ready for that yet. Yeah. The Biot-Savart law is not usually something you touch till the 500 level. So I was like, I don't think I'm quite that gone yet. Well, no, not the 500, maybe the 400 level, but still.